and start recording. Okay. All right. So welcome back. I got an exciting lecture for you today. A couple quick announcements before we get started. First, homework 1 is due tonight at 11:59 p.m. So make sure you turn that in. I have office hours today from 5:30 to 6:30 to answer any last-minute questions you may have about homework 1. And homework 2 will be assigned either tonight or tomorrow after you submit your homework 1s. Okay. Are there any questions before we go on? Any questions other than specific questions about homework 1 problems, unless there is something that's unclear in the instructions for homework 1 that you'd like to bring up for the class? Are there any questions on homeworks? Okay, and homework 2 will be on hydrology for stormwater design, which is what we'll be covering today and for the rest of the next couple of weeks. Okay, great. Any questions? Yes. I believe I'm going to have it due 2 weeks from today. Yeah. Okay. Any other questions? All right. Cool. Well, let's go ahead and get started then. A quick review of what we talked about last time. So last time we began our discussion of hydrology for stormwater design. So we're going to be looking at a lot of the hydrologic processes that inform stormwater design. You need to know at least a little bit of hydrology to be able to estimate how much discharge is going to occur in your urban drainage system, and thus how to design the urban drainage system to accommodate those discharges. Okay. And so we talked about the hydrologic cycle broadly. So how water moves through the urban water cycle, how water moves through urban drainage systems. Just a quick recap, what are some of the components of the hydrologic cycle that you remember from the last time? We drew a big picture with the way that water could move through an urban drainage system. What are some of the components? Just call some out. Okay. Actually, instead of calling something out, can I get a hand? Yes. Runoff. Yes. Evapotranspiration. What else? Channelized flow. Great. What else? Precipitation. Any more? Yes. Infiltration. Okay. So what we're going to be talking about for the remaining 2 or 3 lectures is going to be 2 of those components of the hydrologic cycle. We're going to finish up precipitation today, and for the next couple of lectures we're going to be talking about those 2 big ones that I mentioned last time: infiltration and runoff or overland flow. And we're going to show how you can determine how much water infiltrates and how much ends up as overland flow, which is really important for our urban drainage design. Okay. And last time we also discussed rainfall, how we could estimate it for a given urban watershed through the lens of design storms. And I talked about IDF relationships. Who remembers what IDF stands for? Intensity, duration, frequency. So IDF relationships give us a relationship between the intensity of a storm event, its duration, and the frequency. What does the frequency refer to? Yes. Yes. Yeah, so the return interval of the storm. So how often you can expect a storm of that magnitude to recur. Okay. So last time, at the very end of class, I gave you a way that we could compute the intensity of a rainfall event using this function. So this is how the intensity, duration, frequency relationship is specified specifically for the city of Austin through the Austin Drainage Criteria Manual. You're going to be using this manual a lot in your homeworks and projects to come, so I want to get you familiar with it. But we showed this functional relationship between the intensity of a storm, its duration, and its return interval as parameterized by these 3 parameters, A, B, and C. So given a expected duration of the storm and a given return interval, we can compute the expected intensity. So for a 2-year storm with a 3-hour duration from the Austin Drainage Criteria Manual, we have that A is equal to 45.24, B is equal to 9.339, and C is equal to 0.7399. And at the very end of class, I asked you to compute what the intensity of a storm would be for a 2-year storm with a 3-hour duration in Austin. Okay, so can I get someone to just answer what that intensity would be? Let's just write it out here. Maya, I think you answered last time. So
It was 0.9345.
0.9345 inches per hour is the expected intensity of a 2-year, 3-hour storm event in Austin, specifically in one of the regions of Austin, I believe the South region. Okay, so what would the total rainfall depth be for that storm? I'll give you about 30 seconds to compute this. What would the total depth of rainfall be in inches? So this is a 3-hour storm, right? And we have an intensity of 0.3945 inches per hour. So the total depth of rain that falls is, I got about 2.8 inches. So it's just this times 3, which should be about 2.8 inches. Okay, and last time there was a question about what it means to express rainfall in inches or in terms of a depth. You can basically think if you have, let me just draw this on the other another slide. So rainfall depth, you can basically think of this as if you go outside and you put like a pot or a pan on the ground and it rains over the pot or pan, the depth is, basically the depth of rainfall that would accumulate in that pot or pan. And if you multiply that by the area of the pot or pan, you get the total volume of rainfall that fell. So usually rainfall is expressed in terms of volume per unit area, which is in units of depth. Okay, so we have a method for computing the intensity of a rainfall event for a given duration and recurrence interval. But for the purposes of specifying a design storm, this isn't all that useful in itself. Okay, so let's say we have to go and take this IDF relationship and we have to go and create an input rainfall event for a hydrologic model. How can we do that in a realistic way? So how can we generate realistic rainfall events? Okay, so we have an IDF relationship that gives us an average intensity over a storm event of a given duration. So let's say we have, just a plot of the rainfall intensity, and we have time. So the first way you might think to go about creating a rainfall event is if you have a rainfall event of a given duration and a given time, you can just specify a constant intensity over that interval. Right, that might be the first way to think about going about creating a rainfall event that you can feed into a hydrologic model like HEC, HMS, or SWIM. But is this realistic? No. Real rainfall events, so let's just say that this would be constant intensity. Real rainfall events won't look like this. Real rainfall events will look usually something like this. You have your plot of intensity over time. A real rainfall event will kind of usually start off small and then increase very rapidly and then decrease very rapidly again. Okay, so we need a method of taking our IDF relationship and creating a synthetic rainfall event from that IDF relationship. Okay, and the method I'm going to show you to do that is called the alternating block method, or ABM. Okay, so this is used in many hydrologic models. You'll see this in HEC-HMS, you'll see this in SWIM. It's a method of basically taking those IDF relationships and creating a realistic looking rainfall event out of them. Okay, and you will see this if you go into the options in HEC-HMS and specify how to specify a rainfall event. Often it will be in the form of the alternating block method. Okay. So let me outline the procedure for the alternating block method. This is essentially an algorithm that can be used to create a synthetic rainfall event for a given intensity and duration. I will give you the steps of the algorithm here, and then I'm going to actually go and implement it in code because you're going to need to apply it on homework 2, and I want to give you an overview of the method and how to use it. Okay, great. Okay, so the first step is to choose a recurrence interval. And duration. So we're going to specify the recurrence interval and the duration of the storm, just like we did in the previous example. This defines the total length of the storm as well as the intensity through our IDF relationship. Second, we're going to choose a time interval for binning. Okay. So we're going to take our long storm event and we're going to bin it up into discrete increments. So for instance, we might have a total duration of 3 hours and we will discretize that rain event into 10-minute increments. Okay. The third step is to compute the rainfall intensity for each bin. Okay, so we'll have bins from 10 minutes all the way to our final storm duration. We compute the rainfall intensity for each one of those. Fourth, we compute the total depth of rainfall. For each bin. And this will become more clear when I implement it in a second. Fifth, we compute the incremental depth let me write that out again. Compute the incremental depth for each bin. Okay, so each bin is going to contribute some amount of rainfall depth. We find the incremental difference in the depths between those adjacent bins. And finally, we reorder the incremental depths such that the largest increment is in the middle. The next largest is to the right. The next largest after that to the left, and so on and so on, until we get something that looks like this picture here, okay, with our biggest intensity in the middle the next biggest to the right, the next biggest to the left, the next biggest to the right, the next biggest to the left, and so on and so on. Okay, and what this will do is it'll give you a rainfall time series that's consistent with your IDF relationship on one hand, but it is also realistic in the sense that it is shaped like an actual rainfall event would look. Okay, are there any questions on this process before I go ahead and implement it? Okay, so I think it'll become much more clear when I go to implement it. But if, are there any questions conceptually before I move on? Yes.
Why would the intensity be different for each one?
So the bins will be, so you're binning from 0 minutes to the duration of your total rainfall event. So let's say it's 3 hours or 180 minutes. Each bin will increase incrementally. So you'll have 10 minutes, 20 minutes, 30 minutes, 40 minutes, 50 minutes. You compute the intensity for each of those durations. Okay. It'll become more clear in a second. Are there any questions before I move on? Okay, so I'm going to go ahead and implement this in Python. The reason I'm doing this is because I think it's more clear to show it this way than it will be in Excel, where I'm essentially going to have to click around. It's much easier to implement in code than it is to implement in Excel, which you would largely have to do manually. And also because I want to encourage you to use programming in this class to reuse some of those skills you learned in computer methods. I want to help reinforce those skills and give you a chance to apply them. So with that said, I will go ahead and implement the alternating block method to show you what it looks like. You can reuse this code for the homework if you wish. So if you're comfortable with using Python, you can reuse this code. You can implement it also in any other programming language of your choice, or you can do the problem in Excel. But I will give this code to you as a resource, okay? So the first thing we're going to do, we're going to import our modules. Okay, so we're going to import numpy as np, import matplotlib.pyplot as plt. So these are the numerical Python library and the Python library for plotting. Okay, and we're going to do this for the same storm event we used in our previous example. So we're going to use the same A, B, and C parameters for our storm event. So this is step 1 and 2. We are going to specify our duration and recurrence interval through our A, B, and C parameters. So we have A is equal to 45.24. We have B is equal to 9.339. And we have C is equal to 0.7399. Okay, so that takes care of the first 2 steps of our algorithm. Okay, the next we're going to bin our storm event. So we're going to create bins from 0 to 180 minutes or 3 hours. To do this, we can use the following function. Let's create a variable TD, and let's create an array from 0 to 180 minutes. We want 19 bins. And here's the output. So you can see we've created an array of our different time bins from 0 to 180 in increments of 10 minutes. Okay. The next step is to compute the intensity for each duration in this array. So how can we do that? What is the rainfall intensity for each of these durations? Okay. Yeah, we can go back to our equation, which is given by A divided by TD plus B to the C power. And we get an array of intensities for each of those durations. So we've computed the intensity for each duration. Now note that for 0 minutes, there should not be a positive rainfall intensity, right? So let's go ahead and set that first intensity to 0. So I'm saying select the first element from our intensity array and set it equal to 0. Note that 0 here indicates the first element because we're starting from 0 when we're indexing. Okay. And so now we have an array of intensities. Let's go ahead and plot this. So I'm going to plot TD on the x-axis, intensity on the y-axis. Oops. And this is a plot of our rainfall intensities. On the bottom, we have the durations from 10 minutes to 180 minutes. And on the y-axis, we have our intensity in inches per hour. Okay, so we have an array of intensities in inches per hour. We have an array of durations in minutes. How can we compute the total depth of rainfall for each of these bins? Right. So we can compute the total depth. I think this is our, what step is this? Our 5th step. So we're going to compute the total depth for each. So we have that total depth is equal to the intensities times the durations. And note that our durations are in minutes, so we got to convert it to hours, which we can do by dividing by 60 minutes per hour. Okay, and now we have the total depth. And note that the total depth at 3 hours is equal to 2.8, which is the same total depth that we computed before for the 3-hour storm event. So let's go ahead and plot this. Okay, and this is what the total depth looks like for storm events of duration 10 minutes to 180 minutes for the 2-year storm event. Okay, now the trick here is the following. We have the total depth for a storm for a two-year storm event, going all the way from 10 minutes to 180 minutes. The key here is to recognize that basically a 20-minute storm is 2 10-minute storms. A 30-minute storm is a 10-minute storm plus a 20-minute storm, and so on. Okay, so we can compute the total depth for each bin of our rainfall simulation by finding the incremental depth between each of these bins. Okay, so we want to compute the difference between this first point and the second point, between the second point and the third point, between the third point and the fourth point. And that will give us the incremental depth that falls over each bin of our rainfall simulation. Okay, so we can compute that incremental depth. There's a built-in function in NumPy called np.diff. Okay, so this basically just computes the difference between adjacent elements of your array. So if we look at the documentation here, if we have an array 1, 2, 4, 7, 0, np.diff computes the difference between 1 and 2, which is 1, the difference between 2 and 4, which is 2, the difference between 4 and 7, which is 3, and the difference between 7 and 0, which is -7, and it returns that as our result. Okay, so let's go ahead and do that. This is our step 6. Compute incremental depths. Okay, so our incremental depth is equal to np.diff on the total depth. And let's go ahead and plot that. Here's some of you typing, so I think I'm glad that there's some people following along. It's great. Okay, and what we get is this. So this is the incremental difference between each of these total depths. You can see that the difference between the 0-minute and 10-minute increment is about 0.8. The difference between the next two is about 0.4, and so on. Okay. So note that if we compute the sum of all these elements, it's equal to the total depth of rainfall that fell over our 3-hour storm event. Okay, so this is good, right? We now have a series of increments that we can use to build a storm event that has the same total depth as we wanted for our 3-hour, 2-year storm event, okay? So now is the last and trickiest step. All of the other steps could pretty easily be done in Excel. But now what we need to do is we need to rearrange these bins. We need to rearrange these depths such that the largest one is in the middle. The next largest one is to the right. The next largest one is to the left, and so on until we get kind of a peaking shape in the middle. Okay, so this part is the part that is difficult to do in Excel. Are there any ideas for how we can do this? Any ideas how we can formulate this problem in code? Yes.
First thing I would do is I would make like an array of indices that you want. So like either like the last ones or and then like, you know, if it's like 5 long, there's like 3, 4.
Right. So that would be the array style way of programming this, where you would essentially keep track of the indices, which one is, what the indices are in the current array and where they need to go in the ultimate array. So that's one way of doing it. I'm going to do a way that's, I think, a little bit, one that won't require looking at the numbers as much. What I'm going to do is I'm going to implement this by basically appending to a list. Okay, so in languages like Python and MATLAB, there's different data structures. Arrays are usually of fixed length, whereas lists are variable length and can be changed. Okay, so what I'm going to do is the following. I'm going to create a new empty list called hyetograph. So this is going to store our rainfall array. Okay, and the next thing I'm going to do is I'm going to iterate through each of these increments. And I have to find a way of putting it either on the right or on the left of this list, depending on, yes. Yeah, so what on how are you deciding right or left essentially in that scheme? Whether the number is right, but whether the number is even or odd. Right? You said 1, 3, 5, 7 and 2, 4, 6, 8, right? Right. Right. But there's an even easier way to do it because we can determine whether a number is even or odd. So one way to do that, let me just do this as an aside, is to use the modulo operator. So let's say we do 5 modulo 3, it returns the remainder of that division. Okay, so if we do 5 divided by 5 modulo 2, because the number is odd, it will return 1. If we call 6 modulo 2, it'll return 0 because the number is even. Thus the remainder is 0 when you divide it by 0. So this gives us a way of determining whether a number is even or odd. Okay, so but that logic is basically exactly what I'm going to use here. Okay, so I'll just keep this as a note. Determine if number is even or odd using %. This is called the mod operator. And another thing we can do is we can use a property of lists. So in Python, we have a data structure called a list. And if you have a list and you add it to another list, it combines the two lists together. Okay, so if we have, for instance, if we want to add this list containing 1 to an empty list, it'll return 1. If we want to add 1 to a list 2 and 3, it'll give us 1, 2, 3. Okay, so this gives us basically everything we need to reorder these bins. We're going to iterate through each of these bins. If the number is even, we're going to put it on the left. And if the number is odd, we're going to put it on the right. And from that, we can create our synthetic rainfall hydrograph. Okay, so let me go ahead and implement this. Okay, first, I'm going to compute the length of our incremental depth array. Okay, so there's 18 elements, and I'm going to iterate for each number from 0 to 18. Okay, so I'm going to say for index in range n. Note that if I just do this and I print index, it's going to return all the numbers from 0 to 18. Okay, so I'll say for index in range n, our next depth that we're interested in is going to be, we're going to go to incremental depth, our array, and we're going to select that element. Okay, let's just print next depth here. Okay, so we're going through and we're selecting the elements of this array here. And what do we got to do next? We got to decide if it's on the right side or the left side. Okay, so we can do that by determining whether it's even or odd. We're going to determine whether the index that we're iterating through is even or odd. So I'm going to say if the remainder of index divided by 2 is equal to 0, then it is even. And we are going to take our we're going to take our hydrograph list and we're going to add the next depth to the left. Okay, so we're taking our hydrograph list, and if the number of the index is even, we're going to add it to the left side. Otherwise, we are going to add it to the right side. All right, let's go ahead and run it. And it ran. And let's go ahead and plot the results. And you can see it returned exactly what we wanted. Okay, so we have the largest depth in the middle, the next largest to the right, the next largest to the left, and so on and so on. Okay, so this is how you can create a synthetic rainfall event that you can use for your hydrologic modeling. Again, this is based on our IDF relationships. We created a synthetic rainfall hydrograph that is consistent with our IDF relationship, but also looks realistic. And this is used in models like SWIM and HAG-HMS. Okay, are there any questions? I'll make this code available so that you can use it for your homework if you wish, or reverse engineer it to do this in Excel or MATLAB or any other environment of your choice. Okay, are there any questions on how this was implemented? Any questions? Great. Oh, yes.
Why is this like format better than doing it the other way? That's what I don't understand. That makes sense what I'm trying to say, like,
You
why
mean?
do we want to do it with them on alternate sides?
It's because when you look at an actual rainfall event, it'll generally have a peak in the middle. So it'll start off smaller, get big, and then return back to kind of a smaller depth again.
So you don't have like the data for like time, you just have like,
Yeah, so we have from our IDF relationships what the total depth of rainfall that would fall and the duration. So we can create a realistic looking rainfall hydrograph that matches those parameters using this method. Yeah, so it'll generally look more like this than this. Yeah. Okay, cool. Are there any other questions? Yes.
To find the interval depth, you subtract the differences in the total depth. Is that-
Yeah. So I kind of went through that step quickly, but we have the total depths for each of those durations, and we computed the incremental difference between them using this function np.diff. But you could also loop through and do it yourself if you wanted. Yes.
And that the second graph, where the large increment in the middle, is that second graph how we will model it, where it's kind of like a gradual storm with the peak of the storm in the middle?
Yes. So this is generally how SWIM will specify synthetic hydrographs. Hydrograph meaning a time series of rainfall data over time.
You know, I'm like, we need to treat it as, well, maybe not uniform.
Oh,
Like, I don't know what to call it.
Yeah. So yeah, real hydrographs will look a little bit more messy than this generally. But this is a fairly good approximation. So this is important because when you are modeling stormwater response in HEC-HMS or SWIM, it's important to have the right general shape because a lot of rainfall entering the system all at once has a much different impact than small amounts, entering the system over time. And generally, it's really important to understand how it's going to affect the capacity of your system at any one time, which is why it's important to have realistic looking rainfall events. Yes. Yeah. Cool. So you'll get a chance to do this on your homework. If you want to use Python, you can just use my code and change the parameters that are needed, or you can rewrite it in a programming language of your choice, or you can use Excel. Any one of them is fine. Okay. Okay, give me 1 second to get ready again. All right. So with that, I will conclude our module on rainfall. For the next couple of lectures, what I'm going to be talking about is what happens to rainfall when it lands on our urban watershed. So what happens to rainfall when it lands on the land surface? How much infiltrates into the soil? How much becomes runoff? And how do those values change over time in a way that's going to allow us to design our stormwater infrastructure to accommodate them? Okay, so the title of our next section is Rainfall Runoff Analysis. Okay, this is an extremely important part of urban stormwater design. It's what we spend a lot of our time pulling our hair out over, trying to get this part of the process right, because it's probably the part of stormwater modeling that is the most uncertain. There's a lot of processes in this part of hydrologic modeling that are just not well understood. And it's really important to understand some of those processes so that we can model it better in the future, okay? So in a word, rainfall runoff analysis is concerned with the physical processes that occur within a watershed. And lead to the transformation of rainfall into stream runoff. I'll say into runoff. Okay, so let me draw our picture of a land surface again, just to kind of give you an overview of what we're going to be talking about. Okay, so we have our land surface. We have some channelized flow. We have a water table. And we have precipitation occurring somewhere over this land surface. We have channelized flow. Okay. And then we have a couple other components that'll be of interest to us. The first is the component of rainwater that infiltrates. And the second is the component of rainfall that turns into overland flow. So in addition to these, we also have subsurface flow, which I talked about last time. And for rainfall runoff analysis, we're mostly concerned with infiltration and overland flow, but I want to introduce a few ideas first before I get into just those two components. Okay, so we have channelized flow, we have overland flow, we have infiltration, subsurface flow. All of these types of flow influence the downstream response in the stream, right? And I want to convey to you that a lot of these processes operate at different time scales. So it's important to recognize that first, channelized flow in general travels much, much faster than overland flow. So this is generally 1 to 2 orders magnitude faster than overland flow. And overland flow itself is generally several order of magnitudes faster than subsurface flow. Okay. The ultimate response that you see when you look at the stream flow is a combination of these different types of flow and how they travel through a watershed. So let me give you a quick conceptual overview of runoff as it appears in a stream and how it's affected by these different types of flow. Okay, so let's say we have a watershed. Okay. We have a watershed. We have some streams within the watershed. And in rainfall runoff analysis, we're essentially interested in what happens when rainfall falls over a watershed and how it gets transformed into stream flow at some outlet point. Okay, so let's take a look at the stream flow at this outlet point here for our watershed. Okay, and if you go into that point and you measure the discharge over time, what you get is called a hydrograph. Okay, so this is, when I use the word hydrograph, this is what I mean. It is a graph of the discharge at a point in the channel network over time. Sometimes hydrograph can also be used to refer to the time series of depth over time as well, but in general, it'll refer to the time series of discharge over time. Okay. And so for this watershed here, let's say we have a hydrograph for a given rain event that looks something like this. And this is kind of what it'll look like. Now, the shape of this hydrograph depends on the spatial distribution of your land within the watershed and how rainfall lands within that spatially distributed watershed. Okay, it's essentially the combination of all of the different flow paths that water can take through your watershed when they arrive at the outlet. So let's say we have some raindrop that falls on our watershed and it lands here, right in the channel, very close to the outlet. Okay. This will manifest in a very early part of the hydrograph, right? So this drop of water will end up somewhere right here. It'll be somewhere very early on in the hydrograph. Let's say you have a drop of water that lands maybe somewhere here in the watershed. So this is landing on the channel network, but it's landing close to the middle of the watershed, right? So this will map to somewhere close to the peak, right? Right. If it lands towards the end of the channel network, the drop of water will end up somewhere back here. Okay. If the drop of water lands somewhere near the middle of the watershed, but it doesn't land on the channel, well, then a couple things can happen. One is that it might end up as overland flow. Okay, so this will land somewhere near the middle of the watershed, but it has to travel slowly over the land surface before it gets to the channel, where then essentially it takes this highway down to the end of the watershed. So this, even though it lands near the same location as the one that landed in the channel, this will appear, somewhere a bit further back in the hydrograph. And if a drop of water lands in the watershed and it infiltrates and goes down into the soil, well, if it infiltrates, it'll probably end up somewhere back here, perhaps even weeks to months later on, because water travels much more slowly through the subsurface than it does over the surface. Okay, so when you look at a hydrograph, what this is essentially the distribution of all the different paths that water can take as it travels through the watershed. You can think of a hydrograph as essentially being the histogram of the travel times of the droplets of water as they land in the watershed. So it's important not only to understand where they're falling spatially in the watershed, but also how they're traveling, whether they're traveling through the channel or as overland flow or through the subsurface. Okay. Yes. Yeah, exactly. So that would be essentially the part of the watershed where the most water is arriving at the same time at the outlet. And that will generally be because it's water that's coming from the center of the watershed, kind of in the middle. So that's exactly right. Yeah, you can think of the hydrograph as the distribution of travel times. The most popular travel times essentially will form the peak of the hydrograph. Okay. Are there questions on this concept before I move on? Okay. So with that, for rainfall runoff analysis in particular, we're going to account for essentially just two components of this larger picture. For rainfall runoff analysis, we're going to be concerned with the portion of flow that travels as overland flow and the portion of flow that becomes infiltration. So essentially, how much water infiltrates into the soil and how much escapes infiltration and runs off over the surface into the channel network. Those are the two parts that we're going to be concerned with for the next couple of lectures. Okay. So let's talk about how this process occurs, how we can determine how much water becomes infiltrated and how much becomes overland flow. This overland flow part is really the part that we're worried about because this is what we need to design our stormwater infrastructure around, right? And generally, we want to increase the amount of infiltration and reduce the amount of overland flow, because more overland flow means we need to design bigger infrastructure to accommodate it. Okay, so let's talk about different runoff generation mechanisms. We're going to talk about how we can partition the amount of water that arrives into infiltration and runoff. So first, we're going to talk about it conceptually, and then we're going to put some numbers on it, perhaps later on in today's class. But first, I want to discuss general concepts for runoff generation. There's essentially two different processes two different processes by which runoff is generated. The first is called infiltration excess runoff. And the second is called saturation excess runoff. These are two distinct kinds of runoff generation. Okay. And they happen at different places and at different times. Okay. It's important to understand both of these because you will be dealing with both as a stormwater engineer. Okay, so let's talk about the first kind of runoff generation, infiltration excess runoff. This is also sometimes called Hortonian runoff. You might hear it referred to as Hortonian runoff. And this was kind of the dominant model for runoff generation for a long time. Basically, from the beginning of hydrology up till the mid 20th century or so, this was the process by which scientists thought that runoff was generated. So let's draw our land surface again. Let me get my picture here. Let's draw our land surface again, and we're going to draw what infiltration excess runoff looks like. Okay, so you have your land surface, you have a channel, you have water in the channel, and you have some water table. It comes up like that. Okay. And so let's say we have rainfall falling over the surface of this hill slope. So this is precipitation. So we have rainfall falling over the surface of the hill slope. And as it falls over the land surface, it starts to infiltrate into the soil. So, okay, so you'll get some wetting, you'll get a wetting front that occurs at the top of the soil. And as rain keeps falling, this wetting front grows and grows, and it penetrates deeper into the soil until at some point, the soil becomes so saturated at the top that water can no longer infiltrate into the soil. And any subsequent precipitation essentially lands on the land surface and slides off, and where it then becomes overland flow and travels to a channel downstream. So let me draw that again. Once the surface saturates, the water becomes overland flow and flows downstream. Okay, where it eventually ends up in a channel somewhere. Okay, so note that this surface here, this wetting front, doesn't necessarily interact in any way with the water table. They're two separate zones, essentially. Okay, so saturation in this case occurs from above. And there's a thin layer of saturation at the surface that becomes so saturated that water can no longer penetrate, and it slides off the hill slope into the channel. Okay, so in summary, saturation occurs from above. Yes, so this was the dominant model for runoff generation for a long time, as I mentioned. And this is still the way that runoff generation is implemented in most hydrologic models. So if you use SWIM, or if you use HEC-HMS or other more complicated hydrologic models, it'll usually model runoff generation this way. And it tends to work well for a couple different places. It tends to work well for arid regions, and it tends to work well for urban areas, which is partially why it is still used in models like SWIM, HEC-HMS. But there is another runoff generation process that is separate from this one, that is often the one that is more characteristic of real world conditions. And that is called saturation excess runoff. Okay, so let's draw our land surface again. Actually, let me draw it a little bit better here. Okay, so this time we have the water in our channel. Let me draw it a bit lower, actually. We have the water in our channel. And we have some water table, may rise up. So this is our water table here. And this is our channelized flow. So let's say that we have rainfall occurring over our hill slope just as before. What happens with saturation excess runoff is that the rainfall falls over the hill slope, it infiltrates into the ground, and it keeps flowing downward until it reaches the saturated zone or the water table. Okay, so let's say that this here is at time 1. At time 1, we have our water table right here. The rainfall keeps falling over the landscape until the water level in the water table starts to rise. Okay, so the water table will get higher over time until eventually the water table may burst out over the side and essentially burst out directly over the landscape and cause overland flow to occur directly. So in this case, saturation occurs from below. Okay, we have rainfall essentially recharging the water table rises until it eventually breaks out and travels over the surface as overland flow. Okay. And today, saturation excess runoff is often considered the dominant mode of runoff generation, especially in humid regions. So humid regions being, essentially like the American Midwest, Europe, parts of Asia. In humid regions, saturation excess runoff is generally the dominant type of runoff to occur. Infiltration excess runoff doesn't actually occur as much in practice. The problem with saturation excess runoff is that it's much more difficult to model, which is why many models like SWIM and HEC-HMS don't implement saturation excess runoff directly, because it requires you to keep track of the saturated zone at all times, because that's where runoff is actually being generated. So it's much more computationally difficult to model saturation excess runoff. Okay. Are there any questions on the 2 runoff generation mechanisms before I move on? Any questions on these concepts? Okay. Just want to make a quick note about how this might look spatially. With saturation excess runoff, there's often this concept called variable source area. Okay, so if you have a watershed, for instance, let's just draw all of these the same. And you may have a channel network in there. What will often happen is with saturation excess runoff, when the rainfall lands on the catchment and starts to saturate, you'll see kind of these patches of saturated zone that will build up around where the channel network occurs. And they'll generally stick close to the channel network, although they may also appear in local depressions. Okay, so you'll get patches of saturated soil, and these patches grow and grow as the rain event progresses. So often in a catchment, you'll get these spatial patterns of saturation. Okay. Until eventually they start to cover the whole watershed. And when water lands on these saturated regions, you can basically think of that as being like an impervious area. The water will just directly flow to the channel network if it lands on one of these saturated zones. Okay. Yes.
When all of this, is there anything taking into account like the soil, the rich content of the soil?
Right.
Ratio and stuff like that?
Yeah. We're gonna get to that. I don't know if we're gonna get to it. We'll get to a little bit of it today. I'm gonna take you through the two major models that are used. There's several different infiltration models. The one we're gonna cover are the green amped model and the SCS method. The green amped model is physically based, and it will account for a lot of those parameters like saturated hydraulic conductivity, the porosity of the soil, and so on. Yeah. Yes. Okay. So with that, let's talk about the background behind. I'll just call this the physics of infiltration. I'm going to talk about the physical basis of infiltration. Talk about some of the processes, the physical processes that are occurring with infiltration. And I'm going to introduce the green amped model of infiltration. I don't think we will get to the full green amped model today, but at least to give you the background that you need to understand the green amped model. Okay, so we're going to go back to geotech. Who here has taken geotech? Okay, I think most of you have taken geotech. We're going to borrow some concepts from geotech today. First, let's take a look at just an element of soil. Okay, so we're going to take it down to the very basic level. Let's look at an element of soil. It's going to be this little cube here. All right, so we've got our cube of soil. This is we'll call this direction Z. And we got, let's say we have some little soil grains inside of our cube. Okay, so our cube is filled with soil grains. It's going to take me a little while to draw all these. We'll draw them bigger. Okay. All right, so let's define a couple of quantities. I'm just going to give them names. First, let's define the volume of the sample. So this is our volume of the entire control volume. I'll call it VS. This is the volume of our entire control volume. It's the volume of our entire thing here. Okay, what else do we have in our soil cube sample? What are the different things that are inside of here?
Air, water.
Exactly. So there's three main components. We have our soil grains themselves. We'll generally have some water inside of here that fills this pore space. And generally, it will kind of adhere to these soil particles. Okay, so we got water, and then we also have air inside of this volume as well. So let's go ahead and list all of those. We'll say that VA is the volume of air. inside of our CV. We'll say that VW is the volume of water. And we'll say that VM, this is the volume of the soil grains. Okay. And because our control volume consists of only these elements, we can say that the volume of our control volume is equal to VA plus VW plus VM. Okay, so this is taking it back to geotech. Now, we can define a couple of quantities here that we're going to need. So let's just give these definitions for you. The first is the volumetric soil moisture content. So you may remember this from geotech. I'm going to express this in terms of a variable theta. Theta is our volumetric soil moisture content, and it is equal to the volume of water divided by the volume of our entire sample. Okay, so it's the volume of our sample, the fraction that is encompassed by the water. Let me know if this is too messy here. I'll try to clean it up. Okay, so we have volumetric soil moisture content, and we can also define the porosity. Does anyone remember what the porosity is from geotech? Exactly, it's the volume of the voids over the total sample volume. And what is the volume of the voids in this case? It's basically everything that's not the soil grains themselves. So it would be the volume of the water plus the volume of the air divided by the total volume of the sample. Okay, and let me just pose a question. How are these two quantities related if the soil is saturated? Yes, they will be the same. So if the soil is saturated, the volumetric soil moisture content will equal the porosity. Very good. Okay, let's talk about flow moving through a soil element. We can define also the volumetric flow rate per unit area. It's the volumetric flow per unit area. We'll call it little q. And this will be equal to the total flow moving through our soil element divided by the area of the sample. Okay, so if we go back to our diagram, here. Let's say we have this soil sample here and we have flow moving through it. Okay, so we have flow moving through this face here. By default, by convention, we're going to assume that flow moves up. Okay, so we have flow moving through this soil element. If we take the total flow that's flowing through this surface and divide it by the area of that surface, AS, we'll get the flow per unit area, which we'll call little q. Okay. So this is in units of length, length per unit time. And all the rest of these are unitless. Okay. Cool. Are there any questions on any of these terms before I move on? Yes. It doesn't, it's not actually going up. Just by convention, we're going to define Q so that that's facing up. Yeah. Up is positive, yeah. So, yes.
I was just gonna say a question. Because it's a cube. We assume a direction as long as it's passing through that cross section. Or is it just has to go up?
For the rest of our notes, it'll be defined such that Q is going up. Yeah, we're not going to assume any lateral, we're going to assume no lateral flow. So if it bothers you, you just put a negative sign in front of it. So when we're talking about infiltration, it's going to be going down. So infiltration will be equal to negative Q. Yeah. Yeah. Okay. So what I want to do is taking these variables that we've defined, we can define a continuity equation, just like we did for open channel flow. So just as an aside, for open channel flow, does anyone remember what our continuity equation was? Someone want to raise their hand and volunteer a guess? Yes. That is also continuity, yes. But for the same Fenant equations, do you remember what the continuity equation was? Yeah, flow in equals flow out. And we wrote that as dA by dt plus dq by dx was equal to lateral overflow. So that was for open channel flow. But for our soil element, we can define it essentially the same way. Okay, so for soil, we can say that dAW, so this is the area of the water along the face, the area of the water along the face by dt plus dq by dz is equal to 0, assuming there's no external flow into the system. Okay, so for soil, we can define continuity analogously to how we did for open channel flow. We just switched the direction from X to Z, and we changed the cross-sectional area to the cross-sectional area of just the water. Okay. Great. So one more thing. Note that the volumetric soil moisture content, it's equal to the volume of the water divided by the volume of the sample. You can also express it by just removing the depth dimension. And so you can also express this as the area of the water over one of the faces divided by the area of the sample over one of the faces. Okay, if we do that, we can take our continuity equation, can divide by the area of the sample. And what we get is the continuity equation for soil. Oh, okay, let me just finish writing this. What we end up is with d theta by dt plus d little q by dz is equal to 0. And you can verify that in your notes. We just divided that previous equation by the area of the sample over one of the faces. Okay, so next time we're going to get into the green amps method. If you have any questions about the homework, come see me at 5:30 and I'll be happy to help. And don't forget to turn in your homework